where wonder takes the scenic route and science comes with a blanket and a warm cup of curiosity. Tonight's journey begins with something familiar, something we've all gazed at, maybe whispered to, maybe blamed when we couldn't sleep. The moon, always up there, always watching, sometimes full and glowing like a lantern, sometimes barely a wisp of silver. But have you ever wondered, not just what the moon is, but what it's done to us, to the oceans, to life itself? It's easy to think of the moon as quiet, passive, a cosmic ornament slowly circling above. But the truth is, it's one of the loudest players in the Earth's long story, shaping tides, guiding migration, maybe even deciding whether life had a chance to begin at all. So let me ask you, just for a moment, where are you listening from tonight? Is the moon visible where you are, or is it hiding behind clouds, biding its time? If you find this little space soothing, or if you're just here to drift into dreams with a bit of cosmic perspective, I'd be ever so grateful if you liked the video or subscribed. It helps this channel find more wanderers who need a quiet, thoughtful place to rest. Now, I hope this doesn't keep you awake, but if it does, well, you'll fall asleep knowing something strange and ancient about that glowing rock in the sky. So settle in, slow your thoughts, and let's begin. Because somewhere between moonlight and the deep sea, between craters and coastlines, lies a tale of gravity, chaos, and life that only our moon could have written. 4.5 billion years ago there was no moon, just a young Earth, raw, molten, barely holding itself together, and a collision so violent it nearly ended the planet before it began. But from that cataclysm, something began to orbit, something that would pull and shape and stir the seas. Without it, there may have been no tides, and without tides, perhaps no rhythm, no coastlines, no cycles to push molecules into motion, to nudge chemistry toward biology, no life. But how could a lifeless ball of rock do so much? What power does the moon really have? And how do we know? Let's find out. Sometimes the biggest stories begin with the smallest oddities. In the 1960s, scientists noticed something strange. The moon was moving away. Not fast, just a few centimeters a year, slower than your fingernails grow, but still, undeniably, drifting. As if the Earth and moon were having a quiet breakup. But why would the moon be retreating from us? And what, if anything, had it been doing all this time? To find the answer, researchers looked down, not up. They began to study ancient tidal deposits, layers of sediment shaped by water billions of years ago. These deposits formed rhythmic bands like the rings of a tree or the grooves of a record. They told a story not just of the oceans, but of the moon's pull. Because you see, tides leave fingerprints, and those fingerprints are fossilized in stone. And here's the wild part. Those ancient records didn't show 2 tides a day like we have now. They showed hundreds. Billions of years ago, the Earth spun so fast a day was only 5 hours long. Tides rose and fell like the breath of a sprinting planet. The moon was closer then, looming, massive, its gravity pulling oceans into great bulges that sloshed wildly across the surface. Imagine it, a young Earth spinning under a sky ruled by a much larger moon, dragging vast tides across barren coasts. No continents as we know them, no trees, no whales, just water and rock and an insistent lunar rhythm beating like a distant drum. But to truly understand what the moon has done to us, and for us, we have to step further back, all the way to when it arrived. Roughly 4.5 billion years ago, not long after Earth itself had formed, a Mars-sized body, called Theia, collided with our planet. It wasn't a gentle bump, it was a planetary-scale annihilation. Theia struck Earth at an angle, ejecting a ring of molten debris into space. For a while, Earth had rings like Saturn, glowing with heat, churning, chaotic, and then from that chaos a sphere began to form. It coalesced quickly, geologically speaking, within months or years, not eons. The moon was born not beside Earth, but from Earth. forged from the same material, the same violence, a child of impact, a mirror of destruction. Some call this the giant impact hypothesis. Others simply call it the moon's origin story. The moon didn't begin quietly, and it didn't stay quiet for long. Its gravity immediately began pulling on Earth's molten surface. No solid crust yet, just oceans of lava and swirling semi-liquid rock. But even that flowed under the moon's influence. Earth was still soft, still cooling, and the moon stirred it like a spoon in a thick soup. This stirring slowed Earth's spin. Not all at once, but bit by bit, year after year, the moon's pull created friction, like dragging your hand across a turning globe. That friction turned motion into heat. It caused tides in the magma. Eventually, as the planet cooled, those tides moved from rock to water, and that's where the real magic began. Tides are more than just waves. They are the breathing of the planet. Twice a day, the ocean rises and falls, pulled not just by the moon's gravity, but by Earth's own resistance to that pull. One bulge chases the moon. The other on the far side tries to keep up. It's a dance, and Earth has been doing it for billions of years. But here's something even stranger. Tides might have been essential for life to begin. Scientists believe that early life didn't start in deep oceans or vast lakes, but in shallow, shifting shorelines, places where water could pool, evaporate, concentrate chemicals, and leave behind residue, where complex molecules had time to form, break apart, and try again. Tides created those places. Without the moon, the oceans might have been still, their edges static. No intertidal zones, no tidal pools, no rhythm to move water back and forth, stirring the chemical soup of prebiotic Earth. The moon gave Earth not just movement, but variation. And in variation, life finds its foothold. Flash forward hundreds of millions of years. The moon has drifted farther. The days are longer. Earth's crust has solidified. Continents have begun to drift. Life has taken hold. Microscopic at first, simple, clinging to rocks and sunlight. But even now, tides shape the rhythm of the world. Coral reefs grow in time with the moon. Horseshoe crabs come ashore to mate under full moons. Sea turtles use lunar light as a beacon to find their way to sandy nests. Even human menstruation, some scientists speculate, may have once been synced to the moon's cycle, though modern life and artificial light have loosened that bond. And of course, the tides continue. Every day, all over the planet, the ocean breathes in and out. Shorelines shift, mangroves flood and dry. Estuaries mix fresh and salt water in a lunar rhythm that's older than language. But for all this influence, for all the moon has done and still does, its story is one we almost missed. For centuries, the moon was studied mostly for its position in the sky. Calendars, eclipses, folklore. But only recently, with lunar samples, seismographs and spacecraft, have we begun to piece together the deeper truth, that without the moon, Earth would be profoundly different, possibly lifeless. It stabilizes our axial tilt, the angle at which we spin. That tilt gives us seasons. Without it, our climate would lurch unpredictably. Some believe the moon acts like a damper, keeping Earth from wobbling wildly, like a toy top near the end of its spin. With no moon, there might still be oceans, yes, but no regular tides, no stable climate, no long-term cycles to steer evolution. Maybe no mammals, maybe no humans. So much, from something so seemingly distant. It's humbling, really. And yet the evidence of the moon's influence isn't just written in tides or fossils. It's written in rocks. In Australia's Pilbara region, scientists discovered 3.5 billion-year-old tidal rhythmites, stone layers shaped by ancient tides. Those layers suggest the moon was once about 22,000 kilometres away. Today, it's nearly 400,000. We can see its departure in the rock record, like tree rings measuring the heartbeat of a planet. And if you look at coral fossils, you'll find something just as strange. Some ancient corals show daily growth lines, much like a tree. Fossils from hundreds of millions of years ago suggest that a year once had over 400 days. The days were shorter, Earth spun faster. The moon has been slowing us down, not metaphorically, literally, and it continues to do so, a little more each year. One day in the unimaginably distant future, the moon will drift so far that total solar eclipses will no longer happen. It will take longer and longer to orbit us. Eventually, Earth's rotation and the moon's orbit will lock, a state called tidal locking. The same side of Earth will always face the moon. Days will be as long as months. It sounds surreal, but it's already happened to the moon. It's why we always see the same face, that familiar cratered gaze. So perhaps it's only fair that we return the gesture someday. But for now, we live in a rare and beautiful window. A time when the moon is just the right size, at just the right distance to create solar eclipses. A time when tides still shape coasts. A time when the moon is still close enough to whisper to the oceans and in turn to us, and it's still leaving, slowly, gently, silently, taking its time, just like we are. And that, dear listener, is how the smallest observations, a misbehaving compass, a layered rock, a fossilized coral, can pull us into the vast machinery of celestial influence. The moon doesn't just orbit Earth, it sculpts it. Its gravity tugs at our oceans, its presence stabilizes our seasons, its past may have ignited life itself. And in its slow, silent dance away from us, it leaves behind a planet shaped, quite literally, by its pull. A pull we still feel every time we watch the tide rise, or look up at the night sky and feel just a little more connected. Let's go back again, not just centuries or millennia, not just to temples or tidal rocks, but farther, to a time before the moon carved coasts, before animals swam or crawled, or opened curious eyes to a glowing sky, before plants greened the land or even oxygen filled the air. Back to the young Earth. If you could stand there, if anything like standing were even possible, you'd be greeted by a planet that barely resembles the one we live on today. The continents, as we know them, did not yet exist. The oceans were vast and wild, flecked with volcanic islands that came and went. The sky, thick with carbon dioxide and methane, would have hung heavy and red, painted with haze. No blue, no stars visible, just heat and cloud and a distant sun trying to shine through the chaos. This was a world in formation, still cooling from the inside out. Its surface was a mosaic of violence and patience. Lava flows seeping into proto-seas, mountains rising and falling in spans too fast for geology, but too slow for human eyes. Earth was still finding its shape, and already the moon was pulling on it. Even in this early chapter, when Earth's surface was more furnace than forest, the moon played its part. It pulled not just on water, but on molten rock, the lithic tides they're called, stirring the planet's insides, heating the mantle, possibly keeping the core churning. That churning may have helped generate Earth's magnetic field, a protective shield that would, much later, become vital to life. Without it, solar radiation would have stripped our atmosphere, boiled away the oceans, and turned Earth into something more like Venus. But instead, Earth held on, and the moon may have been part of the reason why. It's strange to think that tides, in their most ancient form, weren't about water at all. They were about rock. But eventually, water came. Whether it arrived with Earth or rained down later from cometary ice, we're not entirely sure. What we do know is that it came early, within a few 100 million years, and when it did, it changed everything. The planet's surface cooled, steam condensed, rain fell, probably for centuries, carving rivers into newborn rock, gathering in depressions, filling basins. The oceans were born. They were not like ours. No coral reefs, no whales, no sandy beaches. Just endless, acidic seas under a dim red sky, sloshing over volcanic plains and lapping against basalt cliffs. And then the tides began. Real tides, water tides. With the moon still close, they were extreme, hundreds of times stronger than today's. Entire shorelines would have vanished under surging waves, only to emerge again hours later. It was chaos, but it was also opportunity. Because where the land met the sea, life began to flirt with possibility. Chemical evolution had been happening in Earth's oceans for some time. Molecules drifting, colliding, breaking apart, recombining. But it needed help. It needed concentration, repetition, a process that could take scattered building blocks and force them into patterns. And so the tide stepped in. With each pulse of the moon, shallow pools formed and dried, mixed and baked. Organic molecules accumulated. Some formed chains, amino acids maybe, or nucleotides, fragile at first, then stable. And then something clicked. A molecule formed that could copy itself, imperfectly, but enough to begin a new story. This wasn't life, not yet, but it was close enough that evolution could begin to whisper. We don't know exactly where it happened. Maybe in a tide pool, maybe in a warm little pond, maybe near a volcanic vent deep beneath the ocean. But what we do know is that life's chemistry, its rhythms, its cycles, its dependencies, bears the fingerprint of the moon. Even today, the salt in our blood echoes the salt of those early seas. As life slowly emerged, it clung first to water. The oceans were a cradle, a constant, a shield against UV radiation and asteroid impacts and the harshness of a still young sun. And yet, even there, life responded to rhythm. Photosynthetic bacteria began to track light and dark. Others rode the rising and falling tides, adjusting their behaviour not just to day and night, but to the pull of the moon. It's easy to forget that evolution isn't just about change. It's about regularity, about knowing, even at a molecular level, that the tide will return. And return it did. For hundreds of millions of years, the moon continued to choreograph the motion of the oceans, and the oceans, in turn, became the stage where life slowly diversified. Single-celled organisms gave way to colonies, colonies to complexity, complexity to the first multicellular animals, soft-bodied creatures that drifted and filtered, wriggled and grazed. They lived on the sea floor or floated near the surface. Some burrowed into the sediment, stirring the ocean's chemistry. Others followed plankton blooms guided by the moon's gravitational cue. By 600 million years ago, some life had grown big enough to leave a mark, not just in the environment, but in the fossil record. Enter the Ediacarans. They were Earth's first animals. Not quite like anything alive today. Imagine soft discs, fronds and quilted ovals sprawling on the sea floor. No eyes, no mouths, just bodies reacting to light, currents, and perhaps tides. Some Ediacaran organisms show growth patterns that appear tied to lunar cycles, a primitive monthly rhythm baked into their biology. This suggests something profound. The moon was not just shaping the world physically, it was entering the genome. The behaviour of living things began to synchronize with the moon's phases. Life wasn't just surviving in a lunar world, it was learning to follow it. Fast forward again, and we meet creatures with limbs and shells, exoskeletons and eyes, trilobites, nautiloids. The Cambrian explosion had arrived, a biological bloom unlike any before it. Life diversified rapidly, experimenting with shape and motion and sense. And still the moon watched. Marine animals began to migrate vertically in the water column, rising and sinking in rhythm with the tides. Coral colonies grew faster or slower depending on lunar light. Even reproduction, the most sacred act of biology, began to follow the moon's cue. Many marine species release their gametes in synchronized lunar cycles, ensuring that sperm and egg meet in the chaos of the sea. Why the moon? Because it is consistent. Its cycle never changes. Its gravity never forgets. It becomes a clock, Not a mechanical one, but a biological one, woven into DNA, whispered across generations. Even today, lunar rhythms persist. Grunion fish in California lay their eggs in sand during high tides after a full moon. The eggs hatch with the next high tide. Horseshoe crabs, nearly unchanged for hundreds of millions of years, crawl onto beaches in perfect step with the lunar calendar. Their mating driven by a moon they've never seen, but always known. Some human cultures followed the same rhythm, marking time by moons, not suns. Even now, some women's menstrual cycles roughly match the lunar month, about 29.5 days. It's not perfectly synchronized, especially under artificial light, but the echo remains. And this sea, of course, still moves. The tides still come and go. Twice a day in most places. Higher during full and new moons. Spring tides. Neap tides. The moon doesn't just orbit. It breathes, and the planet exhales in kind. You could argue, poetically or otherwise, that the ocean is the moon's shadow. Liquid pulled into motion by invisible strings. And yet, it's real. Measurable. Predictable. It sculpts coastlines, carries nutrients, regulates climate. Remove the moon, and Earth doesn't just lose its night-side companion, it loses its pulse. What's even more remarkable is that no other planet in the solar system has a moon quite like ours. Oh, there are moons, dozens, hundreds, but none are so disproportionately large compared to their host. The moon is about a quarter of the diameter of Earth. That's enormous. Most planetary moons are tiny by comparison, captured asteroids or fragments. But our moon was born in fire. It came from us, and perhaps in doing so, gave us what no other world received. Stability, cycles, balance, a chance. This doesn't mean the moon is responsible for everything, of course. Earth is a system of systems. Atmosphere, magnetism, chemistry, plate tectonics, solar energy. But the moon was there at the beginning, pulling, steering, waiting, and we are, whether we notice or not, children of its gravity. It shaped not just the oceans and their tides, but the very timing of life's emergence. It gave us long-term cycles, the kind needed for slow, steady change. It forced the Earth to wobble just enough to have seasons, but not so much that they became chaotic. It turned an unstable, post-impact world into a haven for evolution. We live on a moon-modulated planet, and in many ways, we always have. Look closely at Earth's history, and you'll see this partnership again and again. In the rhythmites of ancient stone, in the bands of fossilized coral, in the migration of fish, in the synchronized spawning of reefs, in the liquid ballet of coastlines, in the soft cadence of waves rolling in under a full moon sky. Even now, astronauts who have walked on the moon describe a peculiar feeling of stillness, yes, and silence, but also of familiarity, as if the moon is not just a destination, but a kind of mirror. It reflects light, of course, but maybe more than that, it reflects history, a history we're still unravelling. And so we return, as we often do on this channel, to something very small and very large at once. A thought that the moon, so often reduced to backdrop, to poetry, to metaphor, may in fact be one of the most consequential players in the story of life, that we owe it more than tides, or calendars, or eclipses, that we owe it the conditions for life to even begin. The Earth without the moon is not just darker, it is different. Maybe unrecognisable, maybe uninhabited. And that is a reminder, quiet but profound, that sometimes the most essential forces in our lives are the ones we rarely think about, the ones that pull without sound, the ones that shape without asking, the ones that leave slowly, gracefully, but never without leaving something behind. If you were to measure Earth's history with a ruler, life wouldn't appear until the last third. Complex life, the last tenth. Human beings, we wouldn't even register as a pencil mark. And yet the moon, our steadfast partner, has been here the whole time, turning an otherwise chaotic planet into something almost rhythmic. But it wasn't just the moon's presence that mattered, it was what the moon did. You see, a gentle orbit may be lovely, but it's friction that sparks change. And the moon has been generating friction from the very beginning. Let's talk about energy. Tidal energy, to be specific. The result of the moon's gravity pulling on Earth's oceans and crust, creating movement that doesn't just push water back and forth, but slowly grinds at the edges of the planet. The continents themselves flex minutely under the strain. This flexing produces heat, not a blaze, but a whisper of warmth, enough to influence currents, to stir the deep sea, to keep Earth's outer shell mobile. Tides affect climate. That part's subtle, but real. As water moves, it carries heat with it. Ocean currents distribute energy around the globe, warming coasts, driving winds, shaping weather patterns. But tides also oxygenate the seas. They churn shallow waters, breaking up layers, allowing gas to dissolve, keeping marine ecosystems alive. Now imagine Earth without tides, or with only solar tides, which are far weaker. The oceans grow still, stratified. Oxygen gets trapped at the surface. Deeper waters become anoxic, oxygen-starved and inhospitable. Nutrients stop circulating, life slows. In some places it dies. In fact, this isn't hypothetical, it's happened before. Roughly 2.5 billion years ago, Earth entered a period of dramatic transformation. Before this time, the atmosphere contained almost no free oxygen. Life was largely microbial, anaerobic, simple, often sulfur-breathing. But then, a new kind of microbe emerged, cyanobacteria, capable of photosynthesis. They consumed carbon dioxide and released oxygen. At first, this oxygen was absorbed by iron in the oceans, forming vast deposits of banded ironstone, red layers still mined today. But eventually, the oceans couldn't hold any more and the oxygen began to leak into the air. This was the Great Oxygenation Event, and it was a disaster. For much of life at the time, oxygen was toxic. It tore apart molecules, it killed. The anaerobic world began to die off. But at the same time, it set the stage for something new. Oxygen allowed for more efficient metabolism, more energy. Larger, more complex organisms, eukaryotes, eventually multicellularity. And through it all, the moon kept stirring the oceans, helping oxygen reach deeper waters, helping this new oxygen-rich world take root. Not alone, of course. Plate tectonics, sunlight, volcanic gases, they all played a role. But the moon's tides ensured that the ocean never went still, that life had room to expand. Fast forward another billion years or so, and life was beginning to stretch toward complexity. The Ediacaran creatures still ruled the seafloor, but the rules were about to change. Around 541 million years ago, something extraordinary happened. Life exploded. The Cambrian explosion, a burst of biodiversity so sudden, so varied that Darwin himself found it unsettling. Creatures with shells, with eyes, with spines, swimmers, burrowers, grazers, predators. Every major animal body plan appeared in the span of a few million years. It was as if life, after eons of quiet experimentation, suddenly unlocked a floodgate of potential. What triggered it? There are theories, and likely no single answer. Rising oxygen levels, evolutionary innovations, ecological feedback loops. But among them is the idea that tidal mixing, still driven by the moon, continued to play a role, keeping coastal environments in flux, creating niches, driving speciation through environmental complexity. The moon doesn't evolve, but it creates the conditions for evolution. It pulls the tides, which expose land and submerge it again. It builds intertidal zones, harsh, dynamic spaces where only the adaptable can thrive. And it brings light. The moon reflects sunlight, of course, but more than that, it gives the night a rhythm, a 29.5-day cycle of light and dark, of fullness and shadow. Many marine animals, even today, use this cycle to time their behaviour. Coral spawning, fish migrations, plankton blooms. It's not just about gravity, it's about predictability. For life to flourish, it doesn't just need energy and matter, it needs rhythm. A sense that tomorrow will resemble today. At least a little. The moon gave Earth that. A reliable tug. A consistent arc across the sky. A monthly cycle of fullness and emptiness. Even after the Cambrian explosion, as life grew stranger and more ambitious, the moon continued to shape the world quietly. As fish evolved in the oceans, their movements responded to tides. As plants crept onto land, they did so at the edges of water, in swamps and marshes that rose and fell under lunar influence. Amphibians followed, then reptiles, then mammals. Even humans, late as we are, feel the moon's hand, in our circadian rhythms, in our calendars, in the tides that still shape coastlines where we build our cities. But there's more, because the moon doesn't just regulate tides, it also stabilizes Earth's axial tilt. Without it, our planet's tilt could vary wildly, from nearly upright to nearly sideways, over timescales of millions of years. This would wreak havoc on the climate. Ice ages could come and go unpredictably. Tropical zones might swing to polar latitudes and back. It would be difficult for ecosystems to adapt, for agriculture to take root. But thanks to the moon, Earth's tilt hovers between 22 and 25 degrees. It wobbles, yes, but gently, predictably. And that means seasons. That means climate zones. That means long-term habitability. In a way, the moon is Earth's climate anchor, and it may explain something else too, the apparent rarity of complex life. We've found thousands of exoplanets, worlds orbiting distant stars. Some are in the habitable zone, with temperatures suitable for liquid water. But so far none seem to have moons like ours. And without a large moon, their climates may be chaotic, their days irregular, their oceans still. It's possible that life exists elsewhere, even common. But complex land-based life? That might require more than just a planet in the right place. It might require a moon in the right place too. And we have one. By accident, by collision, by chance. A moon that once boiled the planet and then cooled it. That once stirred magma and now stirs tides. That once loomed enormous in the sky and now hangs steady and modest. A moon that triggered events without meaning to. That catalyzed change simply by orbiting, pulling, tugging. It is not an agent. It has no will. But it has shaped Earth in ways that make stories and life possible. The moon doesn't speak. It doesn't burn or roar or flash. It doesn't conquer. It pulls. And in pulling, it changes everything. In the moments after that ancient impact, the one that ripped our world open and gave birth to the moon, Earth was raw. Its crust hadn't yet formed. The surface boiled. But the moon, newly born and circling close, had already begun the long work of shaping what came next. What started as tidal forces in molten rock eventually became a planetary heartbeat. First in magma, then in water, then in life. But that first pull didn't just change the oceans, it slowed our planet's spin. That might sound simple. Rotation slows. So what? But in that slowdown lies one of Earth's most important evolutionary tools. You see, early Earth spun fast. A day lasted only 5 or 6 hours. The sun blazed across the sky in a rush. Night fell like a dropped curtain. But with every year, every tug from the moon, our rotation slowed. Days lengthened, slowly, relentlessly, giving the planet more time to radiate heat, to cool its surface, to stabilize weather patterns. A longer day meant gentler temperature swings, more moderate climate zones, and more consistent environments where complex chemistry could settle in and get to work. And not just for one part of the world, for the whole spinning sphere. The moon gave Earth a global tempo, and the changes didn't stop at the surface. Deep underground, the moon's gravitational influence might have helped stir Earth's liquid iron core, the very thing that powers our magnetic field. Without that magnetic field, Earth's atmosphere would have long since been stripped away by the solar wind. No air, no oceans, no life, just a dry, scarred rock like Mercury. But Earth held on, and the moon's quiet hand may be part of the reason why. Let's return now to those oceans, newly formed, planetary in scale, and for a while, lifeless. Just salted minerals, waves and weather. But not still, never still. Not with the moon overhead. The moon kept water moving. It kept shallow seas from stagnating. It created gradients of salinity, temperature, pressure. These gradients became the stage for life's first experiments, the zones where complexity could evolve, and once life began, it faced a challenge: how to coordinate. The ocean was vast. Communication was impossible. Yet somehow, even the earliest life forms began to move in unison, to rise and fall in the water column, to bloom, to reproduce, to migrate. They followed a cycle. That cycle was lunar. Even the first plankton learned to rise at night and sink by day, to glow in response to lunar light, to orient themselves to the moon's place in the sky. They didn't know the moon, they didn't see it as we do, but they felt it, and they followed. This synchronization still exists. To this day, there are coral reefs that spawn only once a year, after the full moon in a specific season. Somehow, entire colonies across vast distances release their gametes within minutes of each other under a silver sky. If they mistimed it, reproduction would fail, but they rarely do. This is not just chance. It is choreography, and the moon is the conductor. But the moon's influence wasn't only felt in water. As life began to crawl toward land, it met a barrier. The harshness of dry air, the violence of ultraviolet light, the inconsistency of rain. And yet in the intertidal zones, those strange in-between places created by the moon's rhythm, life found a bridge. Tide pools, mud flats, estuaries, littoral zones. These environments flooded and dried in regular patterns. They offered nutrients, shelter, and variety, and they trained organisms to handle change, to survive in water and air, to hold their breath, to store moisture, to crawl instead of swim. This is where lungs evolved, where legs first wriggled, where the ancestors of amphibians crept from pool to pool, following the tide line, and still the moon pulled. As animals moved inland, they carried lunar rhythms with them, hidden in genes, in instincts, in behaviours. Some mammals today still ovulate on a lunar cycle. Some predators hunt more during full moons. Some birds migrate in part using lunar light. The moon's fingerprints are in our hormones, our sleep patterns, our biology. We don't always notice, but the body remembers. Even culturally, the moon's influence is ancient and pervasive. For most of human history, we tracked time by its cycle. Months, moonths are echoes of that tradition. The lunar calendar came before the solar one. Festivals, plantings, rituals, all tied to the moon's phases. Our ancestors built monuments aligned to lunar risings, stones arranged to catch moonlight on solstice nights. Pictographs etched into caves with symbols for crescent and full. Long before telescopes or rockets, humans had a relationship with the moon that was intuitive, emotional, ritualistic, and also practical. The moon illuminated the night. It guided the tides. It measured the passage of time, and still it drifted farther away. Every year, the moon recedes by a few centimetres. This slow departure continues to lengthen Earth's days. In the age of the dinosaurs, a day lasted about 23 hours. In the age of trilobites, closer to 21. If Earth survives long enough, eventually the moon's recession will slow and stop, and we'll become tidally locked. One side of Earth will always face the moon. One side of the moon, always Earth. A perfect silent orbit. But that's billions of years away. Right now, we're in a rare window. A cosmic coincidence where the moon and the sun appear the same size in the sky. That's why we get solar eclipses. It won't last. In the distant future, the moon will be too far and solar eclipses will disappear. We are living in a moment, a brief balance between past and future, and that's where we find ourselves, shaped not just by the moon's ancient creation, but by its ongoing departure. A process so slow we never feel it, yet so powerful it has shaped the length of our days, the rhythms of our oceans, the path of life on Earth. Even now, in an age of satellites and space stations, the moon's pull continues, not metaphorically, physically. Tides rise. Oceans churn, continents flex, Earth's spin slows. The moon is still doing what it has always done, not loudly, not urgently, but constantly, gracefully. And that brings us to a final thought about cause and effect. Because in science, we often ask what things are for, what purpose they serve, but the moon wasn't for anything. It didn't come into being to stabilise our tilt, or create tides, or foster life. It just happened. A collision, an accident. But from that accident came order. From that chaos, a clock. From that silence, a rhythm. And from that rhythm, us. We who gaze up, wondering. We who study the tides and measure the moon and place reflectors on its surface so that lasers can bounce back and tell us, yes, it's still leaving, still pulling, still shaping our story. The moon doesn't care. But we do, and maybe that's the point. In a universe full of fire and ice, chaos and collapse, here is a world where a shattered beginning became a steady partner, where a lifeless rock became a guardian of tides, where gravity wrote poetry in water, where the sea, lit by moonlight, carried atoms toward complexity, and eventually complexity toward consciousness. We may never know if it was the only way, if life needed a moon, if another configuration could have worked. But what we do know is this. We got this moon, and it gave us this Earth. The moon is not just a satellite. It's a sculptor, a clockmaker, a partner in the dance of oceans and genes. It gave us rhythm. And rhythm gave us life, not all at once, but pull by pull, tide by tide. The moon doesn't move quickly, and neither do its consequences. A tide doesn't crash like a storm. It creeps, it breathes, it changes the world not in bursts but in beats, steady, slow, and absolutely relentless. And it is in those small, repeated motions that some of Earth's biggest transformations were set in motion. Because once the moon began to pull at our oceans, a chain of cause and effect unfurled that would never quite stop. Let's begin with the obvious, the tides. Twice a day, on most shores the water rises and falls. The moon's gravity pulls on Earth's oceans, drawing them into bulges, one facing the moon and another on the far side. But the Earth spins beneath those bulges, and so the water seems to move. It sloshes around continents, rushes through straits, pushes into bays. It turns coastlines into liminal spaces, places that are neither land nor sea but both in rhythm. These zones are more than just curiosities. They are engines, intertidal zones, places that flood and dry in predictable rhythm, are among the most biologically productive areas on Earth. From mangrove forests to salt marshes, kelp beds to estuaries, they provide shelter, oxygen, nutrients, and access to both marine and terrestrial food chains. Without tides, many of these ecosystems would collapse. But the moon's pull didn't just shape where life could thrive, it changed how it behaved. Imagine an organism living in a tidal zone. Its world transforms every few hours. Underwater, then exposed. Surrounded by salt water, then air. Heat, dryness, immersion, shade. The only way to survive is to adapt, not once, but constantly. To change not just body, but schedule. To live by a clock that isn't the sun's. And so, over time, the moon didn't just create new habitats, it created new pressures. Natural selection began to favour creatures that could time their behaviour to the tides, to know when to retreat into burrows, when to open their shells, when to feed, when to spawn. These weren't conscious decisions, they were biological rhythms, built into genes, passed down through generations. These rhythms persist even today. Put a fiddler crab in a tank far from the ocean, and it will still move in time with the tides, as if it remembers a moon it can no longer see. Horseshoe crabs haul themselves onto beaches precisely during spring high tides, guided by a lunar rhythm older than the continents they walk on. Even plants in tidal wetlands open and close their stomata, in sync with the ebb and flow, responding to cycles of submersion and air. This, perhaps, is the moon's most profound legacy. It introduced time to life. Not in the abstract, not in the ticking of a clock, but in behaviour, in instinct, in biology. Before there were calendars or clocks or watches glowing on our wrists, the moon had already built a schedule into the world. And it didn't stop there. Tides also reshape coastlines. Over millions of years, the moon has played the role of an invisible sculptor, carving estuaries, smoothing shorelines, building deltas, filling and draining basins. These geologic changes in turn influence weather. Tides help mix ocean water, blending surface warmth with deeper cold. This keeps the oceans stratified but not stagnant, a layered system that helps regulate the planet's climate. Let's pause here for a moment, because this is where the chain reaction grows more subtle. A stable climate is not just convenient, it's critical. Life, especially complex life, needs consistency. It can survive in cold, or heat, or dryness, but not if those conditions shift too dramatically, too fast. The moon's role in slowing Earth's rotation and stabilising its axial tilt helped create a climate that was regular enough for life to adapt, to specialise, and to spread. Think of it this way, the moon didn't just stir the oceans, it slowed time. It stretched the day from a frantic 5 hours to a measured 24. That gave organisms more time to photosynthesize, to hunt, to sleep, to grow. It gave evolution room to breathe. But even the moon's consistency can't hold back every shift. Throughout Earth's history there have been moments of upheaval, cataclysms that reset the clock, Snowball Earth, the Permian extinction, the asteroid that ended the age of dinosaurs. Each of these events sent shockwaves through the biosphere, and yet, through them all, the moon remained. A steady hand, a returning tide, a pattern that life could cling to, even when everything else fell apart. In some ways, the moon has been a kind of biological metronome, keeping the tempo even as the melody changed. Let's talk more about these rhythms. Lunar cycles don't just govern tides, they also regulate the amount of light available at night. In the open ocean, where artificial light doesn't exist, the full moon casts a glow bright enough to affect behaviour. Some fish rise to the surface during full moons to feed. Others descend to avoid predators who can now see them better. Zooplankton, the microscopic animals that form the base of many food chains, migrate up and down in response to moonlight, creating what may be the largest daily movement of biomass on the planet. And when these small organisms move, everything else follows. Predators hunt them, nutrients shift. The entire food web pulses with lunar rhythm. Even on land, some animals follow the moon. Lions hunt more successfully during darker, moonless nights. Owls time their calls to moonlight. Insects, confused by artificial lighting, cluster around porch lamps in part because their internal systems evolved to orient to the moon. And then there's us, humans. We may not realise it, but our behaviour still follows lunar echoes. Some studies have found that people tend to sleep slightly less and go to bed later in the days leading up to a full moon, perhaps an ancestral remnant of using moonlight to extend evening activity. Menstrual cycles, while influenced by many factors, still often align with the moon's 29.5-day orbit. Ancient cultures noticed this, of course. They didn't need clinical trials. They had observation, and what they observed was a pattern. The moon rose, the tide came in, the womb quickened, the fish returned, the seeds were sown. All of it rhythmic, all of it connected. It's easy now, in a world of electric lights and 24-hour schedules, to forget that biology doesn't run on the Gregorian calendar. It runs on pulses, on intervals, on cycles shaped by the moon long before clocks began ticking. This is the great quiet truth of the moon's influence. It didn't just set events in motion, it layered them. Water moves because the moon pulls it. Life adapts because the water moves. Behavior changes because life adapts. Ecosystems form because behavior changes. And eventually minds emerge, human minds, capable of noticing that the moon is even there, capable of recording its phases, mapping its motion, writing poetry about its glow, launching machines to visit it, planting flags on its ancient dust. The moon pulled the oceans pulled the land pulled life forward, and life, somehow, pulled itself into thought. The longer you look at the moon, the stranger it becomes, not for how it changes, but for how it doesn't. In a world where mountains rise and erode, where climates shift, where oceans advance and retreat, and entire species appear and vanish, the moon remains. Same face, same cycle, same pale glow, and perhaps that is why it matters so much, because in that constancy, life found something it could trust, something it could build around, something that wouldn't change, even when everything else did. Let's consider what happens when the rhythms break. Roughly 252 million years ago, Earth experienced what we now call the Great Dying, the Permian-Triassic Extinction Event. It wiped out over 90% of marine species and about 70% of life on land. The cause was likely a combination of volcanic activity in what is now Siberia, runaway greenhouse gases, ocean acidification, and global warming. But underneath the devastation, a pattern persisted. The tide still came and went. The moon still pulled on the oceans, and as ecosystems collapsed and food webs unravelled, some organisms still followed that ancient rhythm, as if their biology hadn't yet noticed the world was ending. And maybe that's why some survived. Because after all the fires burned out and the skies cleared, the moon was still up there, coaxing the seas back into motion, and life, small and stubborn, followed. It found a new foothold in those transitional zones, those places where salt meets fresh, where dry meets wet, where predictability still held. Tide pools became sanctuaries, estuaries became laboratories, and through those edge worlds, life reinvented itself again. If extinction is a reset, then the moon is the memory that remains, the background rhythm that doesn't need to start over because it never stopped. This is not a metaphor, it is a literal mechanism. One of the quiet powers of tidal forces is nutrient cycling. As tides rise and fall, they move nutrients from the deep ocean to the shore, from rivers to deltas, from sediments into the water column. They oxygenate stagnant zones. They prevent eutrophication, the deadly buildup of nutrients that can cause algal blooms and dead zones. They move silt, redistribute chemicals, mix temperature layers. Without tides, these processes slow, the ocean stratifies, life gets harder. Now imagine this over hundreds of millions of years. Imagine the moon gently stirring the planet's largest bioreactor, day in and day out. No holidays, no glitches, just gravity playing its long game. Eventually the moon's subtle effects ripple out into places you wouldn't expect. For example, rainfall. Tides influence atmospheric pressure, sea surface temperatures, and ocean currents, all of which can feed into weather systems. They're not the only driver, of course, but they're part of the mix. The moon doesn't cause storms. But it helps prime the oceans for circulation, and circulation helps shape rainfall patterns. And rainfall that carves rivers, that waters forests, that allows civilizations to rise or fall. All of this because the moon pulls. But the story doesn't stop at ecology or weather. It keeps looping back into biology. Some of the most fascinating evidence of lunar influence shows up not in fossils or shorelines, but in genes. Studies have revealed that many marine species, and even some terrestrial ones, have genes that express themselves in cycles matching the moon's orbit. Not just daily rhythms, but monthly ones. These genes control everything from reproduction to metabolism to behaviour. And here's the strange part. Some of these lunar-regulated genes are conserved across species. That means they've been passed down through evolutionary lineages for hundreds of millions of years. They don't all work the same way anymore, but they're still there, sleeping, echoes of an ancient schedule. It's as if life remembered the moon, even when it no longer needed to. Even humans, for all our artificial lights and digital calendars, may still be operating under its influence. Some researchers have found that emergency room visits, seizures and sleep disturbances increase around the full moon. The data is debated, and the effects, if real, are small. But the idea is compelling, that somewhere, deep in the wiring of our brains, the moon still has a key. Not a command, just a nudge, a whisper. And if the moon can influence us, modern, industrial, electric light creatures, then how much more did it shape the creatures who came before? The fish that rose and fell with the tides, the amphibians that timed their migrations with spring moons, the birds that nested by the lunar calendar, the mammals that birthed their young in sync with the phases of light and dark. Evolution doesn't just shape bodies, it shapes timing. And when you change the timing of reproduction, feeding, or sleep, you change everything. You change who survives, who thrives, who disappears, and so the moon becomes a player not just in geology or physics, but in evolution, an invisible hand setting the beat. Let's zoom out again. Because if the moon's pull can guide behaviour, and behaviour guides evolution, then what happens when the moon changes? And it has changed. Not just in distance, but in orbit. The moon's orbit isn't a perfect circle. It shifts over time, affected by Earth's shape, the sun's gravity, and the pull of the other planets. These changes are subtle, slow, measured in tens of thousands of years, but they're enough to modulate tides, to shift climate cycles, to influence the timing of glaciations. Some scientists believe that the moon plays a small but important role in what are called Milankovitch cycles, the long-term wobbles in Earth's orbit and tilt that influence ice ages. The moon helps buffer and shape those wobbles, keeping them from spiralling out of control. And once again, we find the same pattern. The moon isn't in charge, but it's always there, steering slightly, nudging gently. A backstage presence in the theatre of Earth's transformations. Even the development of early human civilizations may have owed something to the moon. The first domestications of plants and animals occurred near coasts and river valleys, places where tides, lunar calendars, and the timing of seasons all intersected. Early farmers watched the moon to predict floods, to plan sowing and harvest, to align their lives with a rhythm bigger than themselves. Over time, that rhythm became myth. The moon was a goddess, a hunter, a clock, a face in the sky, a mystery to revere, and also, eventually, a place to reach. But underneath the symbolism, the physics never stopped. The tides kept moving, and the chain reaction continued. Because the moon never works in isolation. Its influence radiates out, connects, overlaps. It plays a part in climate, yes, but also in plate tectonics. Tidal friction may influence how heat moves through the mantle. That heat in turn drives the movement of continents, the creation of mountains, the opening and closing of oceans. This is not speculative poetry. These are measurable effects. Small, yes, but persistent. And in planetary systems, persistence matters more than power. Over millions of years, tiny forces become dominant players. Imagine a pendulum. If you push it once, it swings, then stops. But if you nudge it gently again and again in time with its rhythm, it swings higher and higher until your small input controls its whole motion. That's the moon. It never needed to shout. It only needed to pull consistently. And the Earth danced in response. Of course, none of this was intentional. The moon isn't trying to help. It has no plan, no motive. It is a rock in orbit, an accident of cosmic billiards. But its influence is real, regardless of intent. And that brings us quietly to one of the deeper truths in science. That meaning doesn't always require purpose. The moon doesn't need to care about life for it to shape it. And we don't need to control a system for it to sustain us. That, in itself, is humbling. Because if the moon could shape oceans, and oceans could shape life, and life could shape consciousness, then perhaps the most extraordinary thing isn't that we're here. It's that we can look up and notice, that we can wonder, that we can ask, how did a silent companion born from fire guide us through water into breath and bone and thought? The moon has no answer. It doesn't speak, but it keeps pulling. Tides continue. Life continues. And the long echo of that ancient impact, the one that almost destroyed us before we even began, becomes, in the end, the thing that made us possible. We came from violence. We found rhythm. And in that rhythm we found time. Real time. Not seconds and minutes, but the living kind. The kind you feel in waves and winds, in the opening of flowers, the hatching of eggs, the migration of whales, the lifting of eyes to a silver sky. Time shaped not by numbers, but by motion, by cycles, by the moon. To understand the moon's role in Earth's story, you have to look not just at the ocean or the tides or even life. You have to look at time itself, not in seconds or years, but in eons. Because the moon doesn't act in moments. It shapes the world across cycles that are vast, layered, and sometimes nearly invisible, until they erupt into change. The thing about Earth is that it forgets nothing. Not truly. It carries the past in layers. Sandstone, limestone, granite, shale. Each one a page in a planetary diary, pressed under pressure, sealed with time. And if you know how to read them, those pages tell a story, not of a single catastrophe or triumph, but of patterns, recurring rhythms, a heartbeat beneath the surface. The moon's role in that heartbeat isn't always obvious. It doesn't leave craters like asteroids or spew lava like volcanoes. But its hand is still there, subtle, insistent, woven into the pace at which life rises, collapses, and rises again. Let's begin with one of the oldest patterns we know. Roughly every 26 to 30 million years, Earth seems to experience a cluster of extinctions. Not just random die-offs, but bursts of disappearance, as if the planet holds its breath, then exhales something new. Paleontologists first noticed this rhythm in the fossil record. They saw that mass extinctions weren't evenly spaced, but came in pulses. Why? That question still echoes through science. Some suggest it's astronomical, the solar system bobbing up and down through the plane of the galaxy, triggering comet impacts. Others think it might be linked to tectonic cycles, or climate feedbacks, or something else entirely. But underneath all these ideas is one steady companion, the moon. While it may not cause these events, it modulates the system they act upon. It determines how stable Earth's climate is, how predictable its seasons are, how well oceans can recover, how quickly life can fill ecological gaps. It doesn't start the fire, but it helps shape what grows back. Let's go back farther, to the time of the supercontinents. You may have heard of Pangaea, the great landmass that existed about 300 million years ago. when all the continents were stitched together like pieces of a massive jigsaw puzzle. But before Pangaea, there were others: Rodinia, Columbia, Kenorland. Each supercontinent rose, drifted, and broke apart in a long, slow cycle called the supercontinent cycle. These rearrangements of land didn't just redraw the map. They rewrote the climate, the ocean currents, and the evolution of life itself. And always, quietly, the moon played along. When continents gathered at the equator, tides behaved differently than when land was scattered at the poles. The shape of coastlines changed how tides moved, where energy was focused, where nutrients pooled. Some configurations encouraged powerful tides that oxygenated seas. Others created dead zones. And so, again, the moon didn't dictate the event, but it influenced the consequences. It's a recurring theme in Earth history. The moon isn't a trigger, it's a tuner. It doesn't strike the chord. It ensures it stays in harmony. Let's look at a moment that seems, on the surface, to have little to do with the moon. The Ordovician-Silurian extinction, about 443 million years ago. One of Earth's big 5 extinction events. It wiped out around 85% of marine species: the trilobites, brachiopods, graptolites. Creatures who had never known anything but warm, shallow seas suddenly faced glaciation and a dramatic drop in sea levels. It's thought that the cause may have been a combination of cooling and falling carbon dioxide levels, perhaps triggered by volcanic activity and changes in continental position. But even here, the moon whispers in the margins. Tides during this period were strong. The continents clustered near the equator, hemmed in by shallow seas. As ice formed and oceans retreated, the tidal zone shrank. Ecosystems that had evolved in the rich, pulsing margins of the ocean suddenly found themselves stranded. The intertidal regions collapsed. Nutrient cycling faltered. Oxygen levels in the water dipped. Species dependent on these rhythms began to vanish. Once again, the moon wasn't the storm. It was the tide beneath it. And after the collapse, when the glaciers melted and the sea returned to the land, the moon returned as well. Its pull re-established the tides. Its rhythm redrew the zones of life, and evolution responded, as it always does, with invention, new species, new strategies, new ways to live on a planet that kept breathing, even after the silence. It's easy to think of extinction as an end, but it's also a beginning. Every great dying is followed eventually by a burst of diversity, what paleontologists call adaptive radiation. New niches open, old dominants fall, the survivors spread out, change, multiply. And in this burst of innovation, the moon provides a scaffold. By re-establishing tidal patterns, it reopens habitats, it rebuilds schedules, it gives life a tempo to match its rebuilding. This pattern plays out again and again. In the Devonian, when forests first spread and fish turned into tetrapods, the moon's tidal zones gave amphibians their first breathing space, literally. In the Carboniferous, when swampy forests covered the land and dragonflies the size of hawks flew above them, the moon's influence on humidity, rainfall and shallow water cycles supported one of Earth's most oxygen-rich periods. And in the Cretaceous, when dinosaurs ruled the land and mammals cowered in the margins, the moon still pulled at the seas, still drove the movements of plankton, still governed the tides that fed the reefs, where life was already diversifying beyond the reach of reptilian giants. Then, 66 million years ago, everything changed. An asteroid struck the Yucatan Peninsula, triggering fires, tsunamis, and a chain reaction that darkened the skies and ended the reign of the dinosaurs. 3/4 of all species vanished, but the tides returned. They always do, and in their return they fed the survivors. The birds, the fish, the mammals, creatures that lived small, bred quickly, adapted fast. In the silence after the impact, the moon offered a pattern that hadn't broken, something steady, something to build around, and life, once more, took the offer. Within a few million years, mammals diversified, forests regrew, Oceans filled with new fish, new corals, new predators, and above it all, the moon still rose and fell, still cast its glow across waves, still drew the oceans in and out like breath. This rhythm, extinction and recovery, loss and renewal, is perhaps the oldest story on Earth, and in each chapter, the moon plays a role, not as hero or villain, but as setting, as atmosphere, as rhythm. Let's pause and think of that rhythm for a moment, because it's easy to focus on the dramatic, the explosions, the extinctions, the floods. But life isn't built on drama. It's built on consistency, on tides that rise every 12 hours, on light that waxes and wanes every 29.5 days, on days that last 24 hours, because the moon has slowed the spin of a world just enough to make time for rest, for wakefulness, for photosynthesis, for sleep. This consistency is rare. In the chaos of planetary physics, it is almost a miracle, and it raises a question we've asked before. Could life like ours have evolved without it? Without stable seasons, would agriculture have emerged? Without regular tides, would coastlines have nurtured the first amphibians? Without the moon's pull, would Earth's axis have stayed stable enough to allow complex ecosystems to flourish for millions of years at a stretch? No one knows for certain. But so far, in all our scans of distant exoplanets, in all the light curves and Doppler shifts and orbit predictions, we have not yet found another world with a moon like ours. Not of this size, not at this distance, not with this influence. Perhaps they exist. Perhaps they're common. Or perhaps the Earth-Moon system is unusually lucky, a rare pairing born from violence that somehow turned into stability, into rhythm, into life. The more we understand the moon, the more it slips from our grasp. It is not just a satellite. It is not just a light in the sky. It is a presence, woven through time, encoded into memory, shaping the world in ways so old we no longer recognize them. The ocean still does. The ocean remembers everything. Its tides, pulsing in and out, are not merely movements of water. They are planetary breath. They are the residual motion of an ancient impact, stretched across 4 billion years of liquid memory. They carried molecules to shorelines, washed them into rock, pulled them back again. They stirred the chemical alphabet, and then they kept stirring, until letters turned to sentences, sentences into species. It is no accident that the earliest signs of complex life appear not in the deep, stable ocean basins, but in the margins, the coastal shallows, where tides shape everything, where the moon is most present. Here, in these zones of disruption, life first learned to take on form. Trilobites with eyes that tracked lunar light, soft-bodied worms that time their burrowing to the phases of the moon, corals that grew in rings, fossilized calendars built not on years, but on lunar months. We find them today encased in limestone. Their daily growth bands are visible under microscopes, and if you count carefully, you can see something astonishing. There are more than 400 days in some of these ancient corals' years. Because Earth spun faster then, the moon was closer, the days were shorter, but the rhythm was already set. The corals followed the moon, even as the planet beneath them changed, even as species rose and fell, even as continents drifted, collided, broke apart again. The moon stayed constant enough for corals to keep counting. The first clocks were not made by humans, they were made by life, and they ran on lunar time. Now imagine all the things built from that rhythm. The synchrony of spawning seasons, the migrations of sea turtles, the full moon blooming of certain plants, the slow opening of anemones. Every behaviour is a response to a cue, and the moon has been cueing life for billions of years. But the moon doesn't just influence life's behaviour, it touches time itself. Many cultures, before and even after written history, used lunar calendars. A month was not an abstraction, it was a phase. You could look up and see the moon's position, its face, its fullness, and know where you were in the cycle. These weren't just primitive systems, they were responsive, elegant, integrated into the rhythm of the planet. The Hebrew calendar, the Islamic calendar, the early Roman calendar, the Chinese calendar, all lunar or lunisolar, all based in some way on the moon's changing face. Some tracked it with pebbles, others with bronze gears, some with stones aligned to moonrises, others with nothing but memory and eyes and the silence of a cloudless night. Even now our word month holds the trace of its lunar origin, a moonth. The Gregorian calendar eventually aligned more closely with the solar year for administrative and agricultural reasons, but even so the moon lingers. Easter, Ramadan, Chinese New Year, Passover, Mid-Autumn Festival. They all move because the moon moves. Human time still dances to its beat, even when we try not to. And beyond that, beyond the rituals and calendars and migrations, is a deeper question, a philosophical one. What kind of world are we living on? What are the chances of a planet like Earth? Not just a rocky planet, orbiting in the habitable zone of a star, but a world with a tilted axis, stabilised by a large moon, a world with liquid water that's kept moving by tidal forces, a world with seasons that change just enough to challenge life, but not enough to extinguish it, a world where life could begin and then keep going. Because starting life, as complex as it is, may not be the hardest part. Sustaining it might be. The moon has helped us do that, by stabilising our wobble, by stirring our oceans, by slowing our spin, by providing a backdrop of rhythm that gave Earth a kind of internal order. This might be rare. Not because planets like Earth are rare, though they may be, but because moons like ours seem to be. Among the thousands of exoplanets we've found so far, few appear to have large, close-orbiting moons. Some may. It's difficult to detect a moon at interstellar distance, but nothing we've found quite mirrors the Earth-Moon pairing, the almost eerie proportionality, the fact that the moon is just the right size and distance to perfectly eclipse the sun from our perspective. A cosmic coincidence, or a subtle filter for life. We don't know, but it means that when we look up at the moon, we are not just seeing our satellite, we're seeing our co-evolutionary partner, a body that has never had an atmosphere, never had life, and yet has influenced ours more than any other object in the sky. Without it, Earth might still be here. But it wouldn't be this Earth. The moon is not just in the sky, it's in our stories, our systems, our seasons, our sleep. It's in the salt of our blood, the rhythms of our hormones, the shape of our coastlines. It has watched every extinction, witnessed every emergence, seen continents drift and glaciers advance, seen forests rise and cities burn, and still it comes, night after night, pulling gently, measuring time, reminding us that not all power is loud, not all change is fast, that sometimes the most important force in a story is the one you forget to name. The moon has never demanded attention. It does not burn like the sun. It does not crash into our lives like an asteroid. It is quiet, patient, predictable, but its influence is deep. Its absence would be felt immediately. In tides that no longer reach the same shorelines, in animals who spawned at the wrong moment, in satellites knocked out of sync, in seasons that began to wobble out of true. Its absence would unravel the rhythm, not all at once, but inevitably, which means that its presence is not just comforting, it's essential. And maybe that's the lesson of the moon. That slow, steady presence can change everything. That quiet rhythm can hold up an entire world, and that some of the most miraculous structures in the universe, like life itself, are not built in fire, but in repetition, pull by pull, cycle by cycle, tide by tide, until something as soft as moonlight gives rise to something as complex as thought. It's easy to think of discovery as something loud, a eureka, a headline, a giant leap. But sometimes it starts with a glance, a moment at the edge of a fire, A pause in the dark, a gaze lifted to a quiet sky. Before telescopes, before science, before writing, someone, somewhere, looked up at the moon and noticed. It changed, that it vanished, then returned, that it seemed to follow them on long walks, that animals behaved differently when it was full, that the sea moved with it, and so began the longest conversation humanity ever had. Not with each other, but with a rock we couldn't reach, circling above, shaping our world in silence. The earliest human interactions with the moon weren't about gravity, they were about meaning. The moon became a clock, a symbol, a character in our stories. The ancient Mesopotamians gave it names, Nana, Sin, and tracked its phases with astonishing precision. They built ziggurats aligned to its risings, not for romance, but for calendars, for planting, for ceremony, for navigation. In ancient China, astronomers recorded eclipses, mapped lunar calendars, and noticed patterns, the kind only visible when you're watching for centuries. The Moon Festival, celebrated to this day, honours that legacy. A festival not of superstition, but of rhythm, of gratitude for the way the moon has always returned. The Greeks were some of the first to study the moon scientifically. In the 5th century BCE, Anaxagoras proposed that the moon wasn't a god or a lamp, but a rock, a world like Earth, reflecting sunlight. A shocking idea, heretical. He was imprisoned for it, but others followed. Aristarchus guessed that the moon was closer than the sun and tried to measure its size by the geometry of eclipses. He was wrong about the numbers, but right about the method, math, observation, deduction. By the time of Ptolemy, the moon had been woven into a system, nested spheres, celestial mechanics, epicycles. Not entirely correct, but clever. A sign that we were trying, that we were willing to use logic as well as awe. Fast forward to 1609, and a man named Galileo took a tube of glass, pointed it at the sky, and shattered centuries of assumption. The moon he saw was not smooth. It was rough, pocked with craters, marked with shadows. It had mountains, valleys, depth. It was not perfect. It was physical. A place. He sketched what he saw, crude by modern standards, but revolutionary. In those smudged charcoal lines, the moon became real, no longer a divine disk, but a partner in the physical universe, an object governed by laws, reachable, knowable, distant, but not divine. Galileo's discovery didn't tell us how the moon formed or what it had done to Earth, but it changed the way we thought about it. It pulled the moon down from heaven and placed it in space, and once the moon was in space, we could start to measure. In the centuries that followed, astronomers refined our understanding of the moon's orbit. They calculated its distance, not in mythic terms, not above or within the realm of the gods, but in kilometres, in metres, in time. Isaac Newton, with his law of universal gravitation, showed that the same force that made apples fall also kept the moon in orbit. He explained tides not as magic, but as the pull of gravity, a force that stretches oceans, bulges water toward the moon, and lets the Earth spin beneath that bulge. This was the first time we truly linked the moon to Earth in a physical, testable way, and it changed everything. Because now, we could connect the moon to motion, to cause, to systems. We could begin asking questions not just about what the moon is, but what it does. The connection to tides was one of the first great insights, but the work wasn't done by Newton alone. Throughout the 18th and 19th centuries, scientists like Laplace and Kelvin and Darwin, George Darwin, son of Charles, expanded on lunar theory. They showed how tides affected not just water, but time. George Darwin proposed that the moon had once been part of Earth, flung off from our planet when it was still molten. He imagined a rapidly spinning Earth bulging at the equator, throwing a piece of itself into orbit. That fragment became the moon. His theory would later evolve. and be replaced by the giant impact hypothesis. But the core idea was stunning, that the moon was not foreign. It was of us, born from the same dust, shaped by the same violence. This wasn't myth, this was geology. And it meant that if we studied the moon, we might learn something about ourselves. The 20th century brought better tools: spectroscopy, seismology, radio waves. The moon revealed itself slowly. We mapped its phases, its orbit, its surface temperature. We tracked how fast it was drifting away, about 3.8 centimetres per year, thanks to laser reflectors left by astronauts. We built observatories in deserts and on mountaintops. We measured how tides influenced ocean currents, how those currents shaped climate, how the moon's presence buffered Earth's tilt. And then we went there. In 1969, Neil Armstrong stepped onto a world without air, without water, without weather. A dead world. And yet a world that had cradled Earth's oceans, slowed its spin, and shaped the rise of life. The Apollo missions weren't just a political victory or a feat of engineering. They were an archaeological dig at planetary scale. The rocks brought back told us stories, not in fossils but in isotopes. They told us the moon and Earth had a shared history, that their chemical fingerprints matched, that they came from the same source, likely the same planet-shattering impact. And so the giant impact hypothesis was born. According to this theory, a Mars-sized object, Theia, collided with the early Earth around 4.5 billion years ago. The collision vaporized rock sent molten debris into orbit and reassembled that material into what would become the moon. An event so violent it nearly erased the Earth. And yet it gave us the conditions we needed to survive. This idea didn't come from telescopes or myth. It came from chemistry, from oxygen isotopes, from titanium ratios, from the quiet, meticulous work of geologists and physicists and lunar specialists. People with microscopes and spreadsheets, people who looked up at the moon and wanted to know why it mattered, and their work didn't stop there. Even today, scientists are discovering new ways the moon shapes us. Astrobiologists study how tides create chemical gradients, necessary for early life. Climatologists model how the moon's stabilizing effect on Earth's tilt kept the planet habitable over long-time scales. Chronobiologists study how lunar cycles influence sleep, reproduction, and circadian rhythms, not just in animals but in humans. Even evolutionary biologists digging through the fossil record find traces of lunar influence: coral growth patterns, shell bands, spawning cycles frozen in stone. Each layer of evidence adds depth. Each scientist adds a verse to a song we've been humming for millennia. And yet, despite all we know, some things remain just out of reach. We still don't know exactly how life began. We still don't know if other Earth-Moon systems exist in the galaxy. We still don't know whether lunar rhythm shaped not just biology but consciousness, the emergence of minds capable of asking these questions at all. But we keep asking. That's what makes the human story so rich. Not just the answers we've found, but the way we never stop looking. The moon has inspired gods, calendars, poems, and rocketry. But maybe its greatest gift has been this. It gave us questions, and then it stayed just far enough away that we had to grow to reach it. The moon may be silent, but our search for its meaning is anything but. After Apollo, you might think the story slowed. The footprints were made, the rocks collected, the flags planted. But exploration doesn't end with arrival. It continues quietly, in labs, in computer models, in sleep-deprived observatories and dusty corners of the fossil record. Because reaching the moon wasn't an answer. It was a new kind of question. One that goes, now that we've stood there, what does it mean? In the years that followed, the moon became something else. Not just a destination, but a lens, a control group for Earth, a mirror. Geologists studied its craters to understand our own planet's bombardment history, because Earth erases its wounds with weather, but the moon does not. Its surface is a gallery of impacts, a museum of violence frozen in time. By counting its scars, we've learned how often asteroids hit our neighbourhood, how frequently chaos knocks on the door, and it's more often than we'd like to think. But more than that, the moon became a tool, a way to track time itself. When we shoot lasers at the reflectors left by Apollo astronauts, they bounce back with extraordinary precision. From those light pulses, we've measured the moon's exact distance and how fast it's drifting away. We've learned that Earth's rotation is slowing, its days lengthening, and we've confirmed, over decades, that the tides really are transferring energy to the moon, lifting it slowly into a higher orbit. It's not poetic, it's physics. But the poetry is still there, tucked beneath the numbers, because every tiny shift in the moon's orbit, every slow outward inch, is part of a vast, ancient exchange of motion between two bodies caught in mutual gravity. Every tide, every wave, every splash on the shore is the moon reaching back. It's not a metaphor, it's a measurable transaction. And that realization that the most delicate rituals of Earth, from tide pools to hormones to sleep, are shaped by something you can point to in the sky, has humbled a generation of scientists. Many of them weren't trained to be poetic, but they became poets anyway, in the quiet margins of their notebooks. Take someone like Maria Zuber. She helped lead NASA's Grail mission, two spacecraft that orbited the moon in perfect tandem, mapping its gravity field in exquisite detail. What they found was astonishing. The moon's crust is not uniform. Beneath the surface, it holds scars, from its birth, from its collisions, from its evolution. But Zuber wasn't just measuring density. She was reading memory. Every gravitational anomaly told a story of magma chambers, of ancient impacts, of crust that fractured and refroze. The moon doesn't have plate tectonics. It doesn't erase, it holds on. And that makes it a vault, a library of deep time. Then there's Sarah T. Stewart. She didn't walk on the moon. She broke things here on Earth, simulating massive planetary collisions in her lab to test theories of the moon's origin. Stewart helped reshape our understanding of the giant impact hypothesis. She proposed that the moon may not have formed from debris that coalesced separately, but from a synestia, a vaporized spinning mass of molten rock and gas that briefly became a kind of planetary donut after the impact. The Earth and Moon formed together inside that shared cloud of chaos. Not mother and child, but twins born of fire. This theory doesn't come from dreamers, it comes from data, isotope ratios, computer models, orbital mechanics. But behind the calculations there's awe. Scientists like Stewart aren't just asking how the moon formed, they're asking how a world comes back together after being shattered, how something broken can still become beautiful. And what does that remind us of, if not ourselves? Of course, not all lunar science is so dramatic. Some of it is exquisitely mundane, tracking the tiny variations in how the moon reflects sunlight, studying how moon dust clings to surfaces, measuring the seismic hum of ancient meteor impacts still echoing through lunar stone. But every one of these details stitches the moon more firmly into the story of Earth, and the people doing that stitching are as varied as the disciplines they come from. Some are planetary geologists, others are climatologists, asking how the moon influences El Niño, ocean currents, and atmospheric tides. Some are evolutionary biologists comparing shell growth in intertidal species across lunar cycles. Others are sleep researchers, scanning brain waves in volunteers to see how their rest is shaped by full moons. Still others are mathematicians refining the equations that predict how the moon will orbit in 1,000 years, or 10,000, or 1,000,000. Because the moon, for all its stillness, is always moving, always changing, always revealing. And perhaps that's why it holds such a rare place in the human psyche, because it's both knowable and unknowable. You can measure its distance with a laser, but you can't measure what it felt like to watch your first eclipse. You can map its surface in nanometers, but you can't map the feeling of sitting under it. barefoot in the grass, knowing it's the same moon that someone loved under 1,000 years ago. This duality between science and story, between data and dream, is what makes the moon so powerful, and it's why the people who study it often sound like poets, even when they speak in equations. Because the moon doesn't just teach us about gravity, it teaches us about patience, about systems that move so slowly we have to measure them across generations, about causes that ripple across eons before their effects are seen, about the kind of observation that requires stillness, repetition, humility. In a world addicted to speed, the moon reminds us some things move best in silence. It also reminds us that collaboration is a force of nature. No one person uncovered the moon's secrets. It took centuries, cultures, continents. It took Babylonian scribes and Chinese astronomers and Arab mathematicians and Copernican rebels and NASA engineers and underfunded grad students staring at databases for hours at a time. It took Apollo's bravado and Galileo's courage and Anaxagoras' exile. It took stories told by firelight and code written in fluorescent labs. It took us, and it still does, because we are not done. There are new missions planned. Artemis, aiming to return humans to the moon. Robotic scouts from India, Japan, the United Arab Emirates, the European Space Agency. There are experiments to see how lunar dust affects human lungs, how gravity, or the lack of it, affects muscle, bone, reproduction. We may one day build habitats there, not because the moon is easy, but because it's close, because it's always been close, a stepping stone, a teacher, a tether, and with each visit we'll learn more, not just about it, but about Earth. Because Earth and the moon are not separate stories. They are one story, told in two voices. One, a planet of air and water and complexity. The other is stone echo of the same beginning. Together they orbit a star. Together they evolve. And between them, stretched invisibly through space, is a thread of gravity that holds their shared memory in place. In the end, perhaps this is what makes the moon so endlessly captivating. Not just that it shapes the tides, not just that it stabilized our axis, not just that it helped make life possible, but that it remembers. It holds the story of Earth in its silence. And we, strange, wandering creatures, have learned to read that silence, to pull meaning from stone, to look up at the sky and say, I want to know more. The moon doesn't answer, but it stays, and that, in its way, is an answer. It's an invitation to keep asking, to keep listening, to keep reaching out, not because the answers are easy, but because the questions are worth it. Because somewhere between the tides and the stars, between a rock and a dream, we are still learning how to hear what the universe has been whispering all along, and the moon is how we began. The deeper we look, the quieter things become, not silent but hushed, whispered in isotopes, encoded in molecules, recorded not on paper, but in stone, in genes, in the slow drift of the moon through 1 billion years of planetary memory. Science, in its deepest form, is not about finding answers. It's about asking better questions. And the moon, though it says nothing, makes us ask some of the most difficult, beautiful, patient questions we've ever learned to ask. Let's start with a piece of rock, not from the moon, but from Earth. A thin slice of ancient coral, cut and polished and examined under the bright cold light of a lab microscope. What you see, if you know how to look, is rhythm, growth bands, layers formed one at a time in response to the rise and fall of tides, the waxing and waning of light. Some of these corals are over 400 million years old. They record more than just the passage of years. They show how many days were in a year back then, and the answer, more than 400. Earth's days were shorter, the moon was closer, but the tidal rhythm was already written into biology. This is geochronology, timekeeping through stone. A fusion of geology and biology that lets us see not just that things changed, but how fast. The moon's retreat from Earth, about 3.8 centimetres per year, is written into that coral, into the growth rings of stromatolites, into layers of mudstone deposited in tidal flats. Every centimetre of moondrift has left a ripple in our rock record, and that's just the beginning. Because the moon hasn't just affected when things happen, it's affected how. Take geochemistry, the study of how chemical elements move through Earth systems. It turns out the moon, by shaping tides and coastlines and continental positions, has played a surprisingly large role in how nutrients cycle through the planet. Think about oxygen. The story of life on Earth is also the story of oxygen. Once there was almost none in the atmosphere. Then, about 2.4 billion years ago, oxygen levels rose dramatically in what we now call the Great Oxidation Event. Why? In part because of photosynthetic bacteria, cyanobacteria, pumping oxygen into the ocean. But also because the oceans were moving, stirring. Oxygen only spreads when water mixes, and water mixes best when there are tides. Models suggest that tidal action may have been essential in distributing oxygen-rich surface water into deeper layers of the sea. Without it, the ocean may have remained stratified, with oxygen above, but anoxic, suffocating darkness below. In other words, the moon helped oxygenate the world. This wasn't a single event. It was a slow, uneven, pulsing transition. Evidence from sediment cores, isotopic ratios of sulfur and iron, trace metals like molybdenum and uranium, all point to a world where oxygen came in waves. Waves pulled in part by the moon. This insight doesn't come from gazing at the moon romantically. It comes from mass spectrometers, clean labs, geochemical proxies that sniff ancient rocks for hints of their chemical past. It comes from scientists asking, what changed the chemistry of the oceans? And discovering again and again that the answer is not just biology or geology, it's tides, its cycles, its rhythm. The moon may have no atmosphere, no water, no life, but it has shaped all three on Earth. Let's go even deeper, into paleogenetics, the reconstruction of ancient DNA, not just from fossils but from living organisms. Some creatures today still carry genetic instructions for behaviour shaped by the moon. Marine worms, for instance, that only spawn during specific lunar phases. Corals that release their gametes in stunning synchronized pulses once per month, precisely after the full moon. The mechanisms behind this timing are complex. They involve circadian genes, the same ones that govern sleep in humans, and lunar-sensitive proteins that respond not just to light, but to gravitational changes. That's right. Some organisms can sense lunar gravity. Not light, not just tides, but the direct silent tug of mass. It's not magic, it's physiology. In certain crustaceans and mollusks, researchers have found mechanosensitive ion channels, tiny protein gates and cell membranes that open and close in response to pressure changes. Subtle shifts in gravitational force, amplified by the body's own structure, seem to trigger responses aligned to the moon's position. That means the moon's gravity isn't just a force acting on oceans, it's a signal received by life itself, and not just primitive life. In mammals, including humans, our sleep, hormone cycles, and even reproductive timing show correlations with the lunar cycle. Melatonin levels fluctuate slightly in sync with the moon. Birth rates increase during full moons in some regions. Anecdotal? Maybe. But patterns persist. And then there's chronobiology, the study of biological rhythms. Daily rhythms are well known, our circadian cycles guided by the sun. But we also have longer rhythms, circulunar cycles, tied to the 29.5-day lunar orbit. Not everyone shows them clearly. Not every individual is tuned the same. But the genetics are there, deep in our evolutionary wiring, like the ghost of a drumbeat we once danced to more clearly. In ancient times, when night was truly dark, the full moon would have been the brightest object in the sky, enough to extend hunting, gathering, travel, rituals. Our ancestors lived lunar time. They aligned their behaviours, their myths, their calendars with the moon because their bodies already had. Modern artificial lighting has dimmed our connection to that rhythm, but not erased it. In sleep studies conducted in natural light conditions, no phones, no bulbs, just firelight and moonlight, people's sleep still aligns with lunar brightness. They fall asleep later, sleep less deeply, just before the full moon. The moon is still in us, and beyond us too. Astrobiologists, scientists who study life beyond Earth, have taken notice. Because if the moon had this much influence on Earth, then it might also be a factor in making other worlds habitable. Large moons may stabilise axial tilt, regulate tides, and provide environmental variability without chaos. They might be filters in the emergence of complexity, not required, but helpful. And so, the question becomes, how many exoplanets have large moons? Right now, we don't know. Detecting exomoons is incredibly difficult. They're small. They don't emit light. Their signatures are subtle, little wobbles in the light curves of their planets, detectable only with sensitive instruments and long-term data. But the search has begun, because if we want to understand how life begins and lasts, we have to understand the rhythms it grows within. And the moon, for all its silence, gave us rhythm, a reliable pulse, a metronome of light and gravity. From this, life built schedules, systems, sleep, time. This brings us to the deepest layer, time itself. We don't often think of time as something shaped. We treat it as a backdrop, constant, linear, absolute. But for life, time is not just what passes, it's what regulates. Organisms need patterns, not just to know when to wake up, but when to divide, grow, reproduce, migrate, molt, mate. Without rhythm, biology drifts, loses efficiency, falls apart. The sun gives us days and seasons, but the moon gives us the middle scale. Not hours, not years, but months. A biological loop, not too short, not too long, that sits in the sweet spot of physiology. Many species reproduce on this schedule because it syncs with tides, moonlight, and gravitational cues. It gives young time to develop in predictable conditions. It links generations to an outside clock. Remove that clock, and the system falters. So the moon, though it may seem passive, is one of the great regulators of life. Its gravity has sculpted Earth's shape. Its tides have stirred the oceans. Its light has guided species. Its orbit has stabilized seasons. And its influence, though often hidden, is everywhere. In coral, in rock, in gene, in dream. This is not mysticism. It's science. The moon is not magical. It's mechanical. But what it makes possible feels like magic, because without it, Earth would be less stable, less rhythmic, perhaps less alive. And without it, we would not be here, standing under its glow, wondering how something so distant could shape us so intimately. When you look at the moon, you're not just seeing a rock. You're seeing a heat map, a fossil, a pendulum, a ruler of invisible things. Because long after the flames of its birth cooled and the magma seas froze, the moon began to take on a new role, not as a creator of life, but as the keeper of its tempo. And some of the most precise records we have of that tempo come not from poetry or tides or myth, but from something quiet, atomic decay. It's called radiometric dating. Atoms, it turns out, are clocks. Some of them, like uranium, potassium, or rubidium, are unstable. They decay over time into other elements, like lead or argon. But they do this at a constant rate, unique to each isotope. Count how much of the original and daughter elements are in a rock, and you know how old it is. The moon, with no wind, no water, and no plate tectonics, preserves these clocks better than Earth ever could. We've used them to date lunar rocks at 4.4 billion years old, some of the oldest solid surfaces in the solar system. They show a world that cooled early, stabilized quickly, and then simply endured. On Earth, that would be impossible. everything is erased, subducted, recycled. But the moon holds on. It's not just a reflector of sunlight, it's a reflector of time. Its surface preserves the deep past in a way no living system can. That's why geochemists and planetary scientists still study those first Apollo samples, because in those grains of dust and crystal are records of heat, impact, and elemental sorting that tell us how planets form. But here's the catch. We don't just learn about the moon, we learn about Earth by contrast. What happens when a world doesn't have plate tectonics, doesn't have a magnetic field, doesn't have an atmosphere? The moon shows us what Earth might have become, without water, without motion, without the ability to forget. Its stillness teaches us why Earth's chaos matters, why our moving plates and storms and rivers make this planet not less stable, but more adaptive. And that contrast is everywhere, in temperature. The moon has no atmosphere to hold in heat. Its days reach over 100 years, or 212 days. Its nights plunge to 170 days, 274 days. That swing, over 250 days between day and night, is called thermal inertia, or rather, the lack of it. Because thermal inertia is a kind of memory, a way for a material, or a planet, to remember the energy it absorbed during the day and release it slowly at night. Atmospheres, oceans, and rocks with high heat capacity do this well. Earth does it brilliantly. The moon does not. Which is why studying its surface temperatures has helped us understand how climates work, not just here, but on Mars, on Mercury, even on distant exoplanets. We model heat flow, dust absorption, radiative cooling. We build simulations of atmospheres on imaginary worlds based on what we learned from the moon. Even its silence is useful. Seismometers placed during Apollo missions reveal that the moon isn't geologically dead, but it sleeps deeply. Its moonquakes are subtle, slow, often caused by the cooling and shrinking of its core. The entire body creaks and contracts, like a wooden ship in cold water. That creaking, mapped over decades, has told us about the moon's internal structure. A thin crust, a solid mantle, a small partly molten core, which in turn helps us model planetary interiors elsewhere. Earth, with its fluid outer core, creates a magnetic field. The moon, with its smaller, quieter heart, does not. But it once did. Ancient lunar rocks contain magnetic signatures, frozen in basalt, hinting that for its first few 100 million years, the moon may have had a powerful magnetic field, perhaps even stronger than Earth's at the time. Why did it fade? How did it work? Researchers are still figuring that out, using magnetometers, rock thin sections, and atomic modelling. But the larger idea is this. The moon is not just old, it remembers being young, and in that memory is a comparative model, a way to test our theories of how worlds age. But perhaps the most subtle and most profound influence of the moon is in the wobble. Earth doesn't spin like a toy top, it wobbles. Its axis tilts at about 23.5 dig, but the tilt changes slightly over time, a motion called axial precession. Left uncorrected, this wobble could swing wildly like Mars, whose tilt varies by up to 60 degrees, swinging it from pole to equator ice ages. But Earth stays steady within a narrow band of tilt. Why? Because of the moon. Its gravity acts like a flywheel, dampening the wobble, stabilizing the spin. This is not a small detail. Axial stability means seasonal stability. And seasonal stability means that life doesn't have to reinvent itself every few thousand years. Without the moon, Earth's tilt might wander over geological time, leading to massive climate swings, snowball events, and desert eras, repeating unpredictably. Instead, it swings gently, a few degrees over tens of thousands of years. Enough to cause ice ages, yes, but not enough to prevent life from adapting. So in a very real sense, the moon gave Earth the stability to become complex, to allow forests, to allow migrations, to allow civilizations to rise in climates that persisted long enough to build memory, story, and agriculture. It's not dramatic, but it might be the most important quiet act in Earth history, because it created a platform, a steady base, for everything else to happen. And it didn't do it with energy or fire or command. It did it with gravity, a pull, a balance, a mathematical whisper across space. We don't often thank gravity, but we should, because without it, there is no orbit, and without orbit, there is no moon, and without the moon, well, Earth would still be here, but not this Earth. Not one with stable days, 24 hours long. Not one with tides that stir and oxygenate oceans. Not one with a biological calendar written in cycles. Not one where a species of upright mammals could learn to tell time by shadows, track seasons by moonrise, and eventually ask softly, what is all this for? Because here's where the science circles back. All these models, these equations, these simulations, they give us insight. But what they give us more than anything is gratitude. Gratitude for chance, for balance, for the long odds that this moon, this distance, this orbit could have lasted this long, this gently. Scientists rarely use the word luck, but behind closed doors in quiet conversations you'll hear it, or cloaked in humility. Because the more we understand about planetary systems, the more we see how rare Earth may be, not just in having life, but in having the conditions for life to persist. And the moon is a part of that condition, a part so stable we almost forgot to notice, but it's always there, pulling, timing, balancing. And all we had to do to see it was look up. Recovery on Earth is never quick. There is no cinematic ending, no fade to black, just time and tide and patience, the slow, quiet work of life finding its way back after collapse. Mass extinctions mark the chapters of Earth's story, the punctuation marks between ages, but they are never the end. They're the turning of a page, and what comes next, every time, is something astonishing. Life, against the odds, begins again. The moon doesn't cause these recoveries. It doesn't rebuild ecosystems or restart photosynthesis or resurrect the lost. But it does something else, something just as essential. It gives the world rhythm. And rhythm is what life uses to rise from the ashes. After the great dying events, whether from asteroid, flood basalt, glaciation, or methane pulses, Earth was often left in silence. Oceans turned anoxic, forests burned, food webs unravelled, but even in that silence the tides never stopped. The moon never skipped a beat. In the darkness, after the asteroid that ended the Cretaceous, when the skies dimmed and the temperatures dropped, and the great reptiles vanished from land and sea, the ocean still moved. High tide, low tide, twice a day, every day, for millions of years. Those tides oxygenated the water, mixed surface warmth downward, kept nutrients in motion when photosynthesis had nearly stopped. They gave plankton a lifeline, gave scavengers a pattern, gave surviving microbes just enough structure to keep going, and they set the tempo for what came next. Life didn't restart with dinosaurs, it restarted with the small things, rodents burrowing in roots, ferns reclaiming ash-covered hills, fish navigating the emptied seas, but across all of them, the moon still pulled, and in that pull it preserved the routines that life could cling to. Patterns that didn't need photosynthesis, or forests, or continents to function. Just gravity. Just the movement of water across a wounded world. Recovery is not invention, it's memory, and memory on Earth is stored in cycles. The moon made sure those cycles continued, and as they did, evolution picked up its brush again. It took time. In the ocean, coral reefs, devastated by acidification and temperature shocks, eventually found new footholds. New species of coral arose, better suited to the changed chemistry. Some partnered with new algae. Others adapted to deeper water. In time, fish returned, crustaceans, mollusks. But always the intertidal zone, that narrow margin between land and sea, was among the first to recover, because it was governed not by climate, but by the moon. No matter the weather, the tides kept coming, bringing nutrients, removing waste, carving space. In those margins, the moon gave life a scaffold, and on land something similar happened. Forests regrew, first ferns, then gymnosperms, then flowering plants. Insects rediversified. Mammals, no longer overshadowed by dinosaurs, began to explore niches left vacant. The moon didn't directly shape that evolution, but it shaped the world those creatures evolved into. By stabilising Earth's tilt, it kept the seasons predictable. Winter didn't migrate wildly across latitudes. Rain patterns stayed within tolerable ranges. Life had enough consistency to develop memory, to anticipate the seasons, prepare, migrate, reproduce. Without the moon, Earth's wobble might have destabilised those patterns, and without pattern, complexity struggles to survive. Because the more complex a species becomes, the more it depends on timing. Think of birds migrating thousands of kilometres, needing food at specific stopovers, nesting conditions to arrive just as insects emerge, temperatures to rise at just the right pace. That only works if spring arrives within a reliable window. That only works if the planet spins smoothly, and the moon made sure it did. This quiet scaffolding, invisible, gravitational, shaped everything that came next. The spread of mammals, the emergence of primates, the birth of forests thick enough to echo with song. Recovery after mass extinction isn't just about surviving, it's about re-establishing systems, and systems need timekeepers. The moon became one. It helped life transition from chaos to complexity, from survival to coordination, from simple cell to ecosystem. In time, those systems grew sophisticated enough to develop behaviours linked to lunar cycles. Spawning events in corals, coordinated across kilometres of reef, timed to the full moon. Mass migrations of fish, aligned with lunar tides. Grunion fish that lay their eggs in sand just above the high tide line, knowing the moon will return in 2 weeks to carry the hatchlings out to sea. Turtles that crawl ashore year after year on the same moonlit nights. Even insects, mayflies, moths, whose emergence synchronises with lunar phases. Every one of these behaviours is a kind of trust, a reliance on a celestial body that has never once broken its pattern. The moon doesn't speak, but life has been listening, and building its rhythms around what it hears. Even in the genetic code, the recovery shows. Species that survived extinction events often carry signatures of ancient bottlenecks, compressed diversity, hints of a narrow path through which life squeezed. Yet they also carry evidence of innovation, duplicated genes, new regulatory patterns, adaptations to tidal pressure, saltwater, night. The moon doesn't cause mutation, but it rewards timing, and so organisms that paid attention to its rhythms often fared better. That's not mythology, that's selection. Rhythms give advantage, cycles shape survival, and the moon offers both. As time marched forward, as the planet warmed, cooled, broke and healed again, this quiet influence never stopped. Even now, recovery continues. In the wake of the Pleistocene, after glaciers scoured continents bare, the tides pulled cold meltwater into motion. They shaped coastlines, built estuaries, fed deltas. Salt marshes returned, mangroves re-established their tangled roots, and again, the intertidal zone became a nursery for fish, for crustaceans, for birds. Today, these ecosystems remain among the most productive on Earth, powered in no small part by the moon. Its rhythm feeds them, gives them definition, and when change comes again, as it always does, the moon will still be there, still pulling, still shaping the margins, still giving life the structure it needs to rebuild. Because here's the deeper truth. The moon doesn't protect us from extinction, but it gives us what we need after. It doesn't stop the fire, but it lays the foundation for regrowth. Its influence is too quiet to prevent catastrophe, but it's just loud enough to support recovery. It's the scaffolding, not the shelter. The breath, not the lungs. The beat, not the song. And without it, the song might never start again. As we stand here today, on a world still healing from ancient wounds and inflicting new ones, it's worth remembering what has always helped us recover. Not just resilience, but rhythm. Not just endurance, but timing. The moon offers us both, not as a gift, but as a consequence of orbit, of impact, of motion set in place long before any eye first looked up and asked, "What is that?" And still, the moon does what it's always done. It rises, it pulls, it turns Earth's water into breath, its silence into structure. And somewhere, in a tide pool, in a reef, in the deep sea, life listens and begins again. Somewhere in the turning of tides, in the repetition of days, in the quiet return of moonlight, something begins to feel personal. The moon was never ours. It doesn't orbit for us. It doesn't pull the ocean with intention, doesn't sculpt coastlines to be beautiful, but still it feels like a presence, not a machine, not a cause, a rhythm. And when you live inside a rhythm long enough, it becomes something more. It becomes meaning. Because what is life, if not rhythm? Breath in, breath out, pulse, sleep, season, cycle. We come from that. We're made of it. And the moon, lifeless, voiceless, cold, has become a kind of conductor, a cosmic metronome. Not because it wants to be, but because it is. And that makes it a strange kind of mirror, because we too shape things without intending to. Our presence leaves a mark, our mass shifts balance, our motion disturbs systems. The moon didn't choose to be born from Earth's trauma, from an impact that nearly unmade a planet. But it stayed, and in staying, it steadied. It became the very thing that helped Earth survive what it had been through. That's not myth. That's physics. But it feels like a lesson. Because here we are, billions of years later, orbiting a planet that was given second chances by gravity, by rhythm, by improbable balance, and we are changing it. Faster than anything before us ever has. Faster than the moon can correct. We've warmed the atmosphere, shifted the carbon cycle, redrawn the coasts. We've added noise to the quiet tempo of Earth's climate, a dissonance the moon cannot quiet. We still have tides, still have seasons, but the rhythm is off. Glaciers melt faster than they can rebuild. Forests burn before seeds can fall. Coral reefs bleach before the moon can call them back to spawn. And all of this blur, this haste, sits in contrast to the moon's stillness, its refusal to rush, its presence, uninterrupted, since before lungs drew breath or leaves caught light. We could call this a warning, but maybe it's something else, a reminder, that endurance is built not from speed, but from pattern, that what lasts is what returns. The moon offers us that reminder every night. No speech, no threat, just presence, which, in a world of noise, is its own kind of wisdom. And yet, the moon is not perfect. Its gravity doesn't solve everything. It can't stop extinction, can't reverse warming, can't hold back floodwaters rising from melted ice. But neither can we, not alone. What we can do is choose what kind of presence we want to be. Not controllers, not conquerors, but participants, things with gravity, things with rhythm. The moon teaches us that influence isn't about power, it's about persistence, about being in the right place at the right time, with just enough pull to shape something else, gently, consistently, over time. And maybe that's our role now, to become more like the moon, to learn the pace of recovery, to stay steady in a world spinning faster than it was meant to be the kind of force that doesn't dominate but supports. Because if the moon could hold space for life to grow from ash and ocean, maybe we can too. not by remaking the world, but by returning to a rhythm that's already there, a pace life understands, one of seasons, not quarters, of renewal, not extraction, of long arcs, not short gains. There's humility in that, a humility we've mostly forgotten, but it's still there, in tidal flats, in coral rings, in moonlit waves that lap against the shore like a memory. The moon has seen Earth break and heal and break again. It doesn't interfere, but it holds the line, and in that way it's one of the quiet heroes of our story. Not because it fixed anything, but because it stayed. When we look at it now, from rooftops, from observatories, from orbit, we're not just seeing a rock, we're seeing a survivor, a co-conspirator, a body that turned a cataclysm into a rhythm, and gave Earth just enough balance to try again. That's not metaphor, that's geology. But maybe it's more, because what the moon really gives us, more than light or tides or stability, is a question. What do we choose to orbit? Where do we place our gravity? And will our presence, like the moon's, give life a better chance? It doesn't take much, a few centimetres per year, a steady tug, a refusal to drift too far away. And over time, even that becomes a force strong enough to shape oceans, to rewrite atmosphere, to offer rhythm to chaos. In a world that needs rhythm more than ever, the moon won't save us, but it's been showing us how to save ourselves for 4.5 billion years. We just have to listen, and then act, not quickly, but with intention, with patience, with gravity. Because this Earth, as lucky as it is, isn't guaranteed. Its climate can swing, its coasts can vanish, its systems can crash. And yet, with rhythm, with pattern, life comes back. We know this, because it's happened before. And the moon was there every time, a scar in the sky, a circle of memory, a lesson drawn in stone. And maybe, just maybe, a reason to believe that the rhythm can still return, if we slow down enough to hear it. And so we return, not to an ending but to the place we began, looking up at a pale, round stone circling above the blue, a companion we didn't choose but one that's shaped nearly everything we know. The moon doesn't ask for attention, it never has, but it has always deserved it. It shaped our tides but never asked for praise. It stabilised our planet but never demanded worship. It gave us rhythm and let us take the credit, and still, every night it rises, sometimes a sliver, sometimes full, always patient, and always there. Maybe that's the quiet gift of the moon, that it shows up, even when we forget to, that it keeps Earth honest, that it pulls gently, like a parent's hand, guiding the planet back towards something like balance. And maybe that's our role now too, to be a rhythm others can rely on, to show up without needing applause, to leave space for tides to work. So whether you're listening from a city rooftop or a quiet bedroom window, whether the moon is above you now or hidden behind clouds, I hope you feel a little more connected to it, because it's not just up there for astronauts and telescopes, it's part of your story, of my story, of Earth's story.